Welcome to another deep dive. Today we're going to be exploring a question that might seem pretty basic at first glance. What is space actually made of? I mean, you might think, well, isn't it just empty?
Right.
But as we're going to see today, it's way more complicated.
Yeah.
And honestly, a lot more fascinating than that.
Absolutely.
We've got some source material here that really dives into this idea, and I think it might blow your mind a little bit.
Yeah.
That space might actually be some kind of elastic solid.
Yeah, you're not alone if you think that sounds kind of strange.
Yeah.
The nature of space has puzzled thinkers for centuries.
Yeah.
Really going all the way back to the ancient philosophers, to modern physicists. Everyone wants to know, what is the stuff that we call space?
Yeah.
And the idea that it might be a substance, even an elastic one, has a long and rich history.
So, okay, let's unpack this elastic solid idea a little bit. What's that even mean? Is space like a giant cosmic trampoline?
Well, not exactly. But the trampoline analogy, I think it gives us a good starting point.
Yeah.
It's a way to sort of picture it.
Yeah.
Imagine instead of space being completely empty, a void,
Right.
that it's a medium with a certain springiness to it.
Okay.
Or a resistance to being deformed in some way.
So, like, you can stretch it, but it'll bounce back, kind of.
Yeah.
Yeah.
That's the basic idea. And this concept was really helpful for early scientists when they were grappling with things like the behavior of light.
So how did they connect an elastic solid to something as intangible as light?
I think it helps to think about how sound waves travel through the air.
Okay.
You know, they cause air particles to vibrate.
Right.
Back then, physicists often imagined light traveling through space in a similar way.
Okay.
So it's almost like causing ripples or disturbances in this elastic medium.
I see. So they thought light was kind of like a wave propagating through a substance?
Yeah.
Like waves in the ocean.
Exactly. Like waves in the ocean. So that analogy helped them explain things like refraction. Okay. You know, when light bends as it passes from one medium to another, like from air to water.
Right.
They figured something similar must be happening as light traveled through this substance of space.
Interesting. Okay, that makes sense. But I know there was a pretty famous scientist, John Mitchell.
Yes.
Who had some pretty interesting thoughts about light and gravity, too.
Absolutely. John Mitchell was an 18th century thinker.
Okay.
And he was one of the first to propose the concept of what we now call dark stars.
Okay.
These are objects that are so massive and so dense that their gravity is strong enough to trap even light itself.
Wow.
He even theorized that you could detect these dark stars by observing their gravitational effects on nearby visible stars.
So he was basically thinking about black holes.
Yeah.
Centuries before Einstein.
Exactly. He was way out of his time.
That's amazing.
Yeah.
But how does this tie back into this elastic solid idea?
Well, you have to remember that Mitchell's ideas, along with all of his work on gravity and the bending of light, it was very much a product of his time.
Okay.
Back then, physicists often relied on analogies, and particularly they used the analogy of an elastic solid to try and conceptualize how gravity could act over these vast distances and how light could travel through this seemingly empty expanse of space.
So they were trying to find a mechanical explanation for these forces that they were observing.
They were trying to fit these new observations into the framework of Newtonian physics.
Okay.
And the concept of an elastic solid offered a way to visualize how gravity could be a force acting through a medium, much like sound travels through air.
Okay, so are there any specific examples of how they tried to apply this elastic solid model to explain things we see in the universe?
Yeah, one really interesting example is how they tried to explain the speed of light.
Okay.
They imagined that the rigidity of this hypothetical elastic medium actually determined how fast light could travel through it. So the stiffer the medium, the faster the speed of light.
Wow. It's amazing how they tried to use this model to explain such a fundamental property of the universe.
It is. It really shows you how powerful analogies can be in helping us understand complex concepts.
Right. But were there any problems with this elastic solid idea?
Oh, yeah.
Did it hold up under scrutiny?
Well, it definitely ran into some serious challenges.
Okay.
One of the biggest challenges was trying to reconcile the rigidity that they needed for light to travel so fast with the apparent emptiness of space. You know, we see planets and stars moving freely without any noticeable resistance.
Yeah, that does seem like a contradiction.
Right.
How could space be both firm enough to transmit light at such high speeds, but also offer practically no resistance to the motion of these giant celestial objects.
That's a conundrum they couldn't quite resolve.
Yeah.
They really struggled to find a model of this elastic medium that could satisfy both of those seemingly contradictory requirements.
It makes sense.
Yeah. I guess it's a pretty tough problem to solve.
It is.
Yeah.
It was one of the big mysteries that they were grappling with at the time.
That makes sense.
Yeah. And those challenges weren't the only ones.
Right.
As physicists continued to study light and gravity, they began to uncover phenomena that couldn't be easily explained by this simple model of an elastic solid.
Like what?
Well, one of the biggest mysteries was the way that gravity seemed to bend light.
Okay. Yeah.
We touched upon this with John Mitchell's dark stars.
Right.
But the full story is even more fascinating.
So tell me more about this bending of light.
Sure.
I know Einstein had something to do with it, right?
You're right. Einstein's theory of general relativity really revolutionized our understanding of gravity and its effect on light. But even before Einstein, physicists knew that light didn't always travel in perfectly straight lines.
Oh, really?
They had observed that light from distant stars seemed to bend slightly as it passed by the sun. So even Newtonian physics predicted some bending of light.
Yeah, to some extent.
I always thought that was purely an Einsteinian concept.
It is true that Einstein's theory predicted a much stronger bending of light than Newtonian physics.
Right.
But the idea that gravity could influence the path of light wasn't completely foreign to Newtonian thinkers. They just explained it differently.
How so? How did they explain it using this elastic solid model?
Well, they imagined that the elasticity of space itself was affected by the presence of massive objects, like the sun. So the sun's gravity, they thought, would create a kind of dent or a curvature in this elastic medium.
I see.
And light traveling through this curved space would naturally follow a bent path.
So they essentially attributed the bending of light to a change in the properties of the medium itself.
Right.
Rather than a direct force exerted by gravity.
Exactly.
That's interesting.
And while this explanation was ultimately incomplete, and it couldn't account for the full extent of light bending that was later observed, it shows how scientists were trying to use the concept of an elastic solid to make sense of these intriguing phenomena.
It's a testament to their creativity, for sure.
Yeah.
And how they try to fit these new observations into existing frameworks.
Yeah, absolutely.
But it also highlights the limitations of those frameworks.
Yes.
And how they sometimes need to be completely reimagined.
Exactly. And that's precisely what happened. With the arrival of Einstein's theories of relativity, Einstein's revolutionary insight was that gravity isn't a force acting through a medium, but rather it's a manifestation of the curvature of space-time itself.
So instead of picturing space as a substance being deformed by gravity, we should think of it as a fabric that's warped and curved by the presence of mass and energy.
Precisely.
That's a big change.
It was a huge shift in perspective. And it really changed everything.
So does that mean the elastic solid model of space was completely abandoned after Einstein?
Well,
was it just a dead end?
It's true that Einstein's theories presented a major challenge to that classical concept of space as an elastic solid. It proved to be very difficult to reconcile the idea of this springy, elastic space with the smooth, curved space-time of relativity.
But you said earlier that sometimes revisiting these old ideas can spark new insights.
Yes.
Is there any way that this elastic solid model might still be relevant in modern physics?
That's a great question. And the answer might surprise you. While the classical model has been largely superseded, there are some tantalizing hints that some aspects of it might not be entirely off the mark.
You've got my attention now.
All right.
Tell me more.
What are these hints? Well, let's venture into the realm of quantum gravity for a moment. This is one of the biggest mysteries and frontiers in modern physics. Quantum gravity seeks to unify Einstein's general relativity with the world of quantum mechanics. These are two incredibly successful theories, but they seem to clash at the most fundamental level.
I've heard that those two theories are like two pieces of a puzzle that don't quite fit together yet.
That's a great analogy. And one of the key areas where they clash is in their description of space-time.
Okay.
General relativity describes space-time as being smooth and continuous.
Right.
But quantum mechanics suggests that at the tiniest scales, the world is grainy and quantized.
So, like, instead of being a smooth, continuous fabric, space-time might be made up of tiny building blocks.
Exactly.
Like pixels on a screen.
Exactly, like pixels on a screen.
Oh.
And this grainy, quantized nature of space-time could potentially lead to some surprising effects.
Like what?
Well, some physicists speculate that this discrete structure of space-time might give rise to emergent properties that resemble the elasticity of the older models.
So instead of space itself being an elastic substance, this elasticity could emerge from the way these tiny building blocks of space-time interact with each other.
That's one intriguing possibility.
Right.
It's kind of like how the seemingly smooth flow of water emerges from the interactions of countless individual water molecules.
Wow. That's really mind-bending.
It is.
So even though the classical elastic solid model is no longer the prevailing view, it might still hold some clues about how space-time behaves at the quantum level?
It's a fascinating thought, isn't it?
It is.
And it shows how exploring seemingly outdated ideas can sometimes lead to unexpected connections and insights.
Absolutely.
It also reminds us that our scientific understanding is constantly evolving.
Right.
And what seems like a dead end today might open up new pathways tomorrow.
That's a good point. Wow. So we've gone from picturing space as this like elastic solid to this idea of it being a smooth, curved fabric, according to Einstein. And now we're talking about tiny building blocks and quantum foam.
Right.
It's a lot to take in.
It is.
Where does this leave us in our quest to really understand what space is made of?
Well, it's definitely a journey with many twists and turns.
Yeah.
But what's really exciting is that we're starting to see potential connections between these seemingly disparate ideas.
Okay.
The concept of an elastic solid, while not a perfect model, it might offer some hints about the emergent properties of space-time at the quantum level.
So it's like those old maps that explorers used to use. You know, they weren't completely accurate, but they provided a starting point.
Yeah.
And help to pave the way for more detailed and precise maps.
Exactly. The elastic solid model might be a bit like that.
Okay.
It might not be the final answer.
Right.
But it helped to shape scientific thinking.
Yeah.
And might still hold some valuable insights.
So if we entertain this idea that the elasticity of space could emerge from this quantum structure, what are some of the implications? What could this tell us about how the universe works?
Well, one intriguing possibility is that this emergent elasticity could actually play a role in the expansion of the universe. We know that the universe is expanding at an accelerating rate, and dark energy is thought to be the driving force behind this acceleration.
Right. Dark energy is one of the biggest mysteries in cosmology.
It is.
We know it's there.
Yeah.
But we have no idea what it is.
Exactly. And some physicists speculate that this emergent elasticity of space-time could be connected to or even contribute to the effects of dark energy.
So instead of thinking of dark energy as some mysterious separate entity, it could be a manifestation of the way space-time itself behaves at the quantum level.
It's a fascinating idea, isn't it?
It is. It's like the universe is a giant self-stretching rubber band.
Yeah.
And this stretching is driven by the quantum properties of space-time itself.
That's a great way to picture it.
Okay, now that's a mind-blowing image.
Yeah.
But what about all the other stuff in the universe?
Right.
Like matter and radiation. How do they fit into this picture of an elastic quantum space-time?
Oh, that's where things get even more complex and exciting.
Okay.
We know that matter and energy warp space-time.
Right.
According to Einstein's general relativity.
Right.
But if space-time also has this emergent elasticity at the quantum level, then the interplay between matter, energy, and space-time becomes even more intricate and dynamic.
So it's not just that matter warps space-time, but the properties of space-time itself could also influence how matter behaves.
Exactly. It's a two-way street. And understanding this intricate dance between matter, energy, and space-time is one of the biggest challenges and opportunities in modern physics.
This deep dive has definitely opened my eyes to the vastness of the unknown.
Yeah.
It seems like every answer we uncover just leads to even more questions.
That's the beauty of scientific exploration. And while we might not have all the answers yet, I think we've gained a deeper appreciation for for the mystery and wonder of the universe.
Absolutely.
And the incredible ingenuity of those who seek to unravel its secrets.
I couldn't agree more. We started with a pretty simple question.
Yeah.
What is space made of?
Right.
And it's led us on a journey through elastic solids, curved space-time, and quantum foam.
It's been quite a ride.
It has been. Who knows where our quest for knowledge will take us next?
The possibilities are endless.
Yeah.
And that's what makes this journey so exciting.
Absolutely.
We're constantly pushing the boundaries of our understanding. And each new discovery brings us closer to a more complete picture of the universe and our place within it.
This deep dive has given me a lot to think about.
Good.
And for all of you listening out there, we encourage you to keep exploring these ideas.
Absolutely.
What do you think space is made of?
Yeah. What are your thoughts?
Let us know. Until next time, keep questioning.
Keep wondering.
Keep diving deep
into the mysteries of the universe.